So hello friends, this is Kaustu Pathare again with a new video. Today in this video we are going to teach a new lesson, a new standard 12th standard mathematics continuity. So welcome to our channel Making Maths Easy. So let's get started. So what you know about the continuity? Whenever we say that a particular function, let's say f of x is the continuous function. So what is it? If f of x is continuous, it is continuous at a, b, c, d, e, and etc. and so on. Let's say f of x function f of x is continuous. Then if I say that f of x is continuous, it should have a constant point. So f of x must be continuous at a. Let's say that f of x is continuous at a. So a must be a constant value or any constant or any variable where the particular function f of x is continuous. Or let's understood this part with the help of graph. So this is our graph. This is a x-axis, y-axis, and O is the origin, and this point corresponds to x equal to a, and this point corresponds to y equal to f of x. So uh, y y is the function, means y corresponds to the function of x where it is x is equal to a, where a instead of a, so this line or this segment is equal to f of a. So here y is equal to f of x. So f of x, we can say that f of x is continuous at x equal to a. So we can write it as, we can say f of x is continuous at x equal to a. So let's come to the some properties of continuity. First property, uh, if a function f is continuous at x is equal to a, if and only if f of a exists such that lim of x tends to a into f of x is equal to f of a. We can say that f is said to be continuous, or a function is said to be continuous if it two conditions are applied. First condition is, uh, first condition here is f of a exists. F of a exists in such a way that the limit of x tends to a, limit of x tends to a, limit of x tends to a into the f of x equal to f of a. And the second condition is negative and positive coordinate, or negative or positive side. Let's say this is a, let us take an example of graph. So this is our graph. In this case there are two major possibilities. One major possibility is the right hand side of f of x, means this is f of x, and right hand side of the f of x means the negative quadrant, or we can say the second quadrant, and left hand side of the f of x means the f of x, this positive quadrant or positive. This is, we know that quadrant 1, 2, 3 and 4. So this is 1, this is 2, this is 3 and this is 4. So this is left hand side, this is right hand side. So in order to prove the limit, or in order to satisfy this condition, second condition is lim of f of x at x tends to a minus equal to a minus at f of x equal to lim of x tends to a plus, which is equal to f of x. So we can say that f of x which is equal to f of a. So we can say that if f of x should be continuous at x is equal to a, if and only if these two conditions exist. Means this second condition means, suppose this is a graph, and we have the positive quadrant, the negative quadrant. In the positive quadrant, we have f of a, lim of x tends to a plus. Okay, lim of x tends to a plus, which is this, x tends to a plus, lim of x tends to a plus. And in the negative quadrant we have lim of x tends to a minus. So these two conditions uh, are equal. If these two conditions are equal, if the negative side as well as positive side simplifies the equality condition, so we can say that f of x is continuous at x is equal to. So if these two conditions are not satisfying, so we can say that f of x is discontinuous at x is equal to, f of x is discontinuous at, f of x is discontinuous at x equal to a, uh, if these two conditions are not satisfying. So the second property is, if function f is such that f of x and f of a both exist, then lim of f of x is equal to f of a, then it is continuous. We know that this first condition. And if uh, the function both lim of x tends to a, f of x is equal to f of x, f of a, then the condition is continuous. And if lim of x tends to a into f of x is not equal to f of a, then the uh, f is said to be having a removable discontinuity at x equal to a. So this continuity can be removed using redefining the function as x equal to a as f of a equal to lim of x tends to f of x. So let's prove it. Uh, consider a function. Consider a function f of x. So we know that lim of x tends to, lim of x tends to a, f of x equal to f of a. So this is the first property. And if I say that lim of f of x is not equal to f of a, then what you can say? So we can say that f of x, f has said that the removable discontinuity at x equal to a. So it has a removable discontinuity at x equal to a, at x equal to a. So this discontinuity can be removed by redefining the function. This can be removed by redefining the function at x is equal to a. So we can put x equal to a and we can remove the discontinuity. So we will get f of a become equal to lim of x tends to a and f of x. So this is the second property. Now the third property, if f of x has irremovable discontinuity, means a discontinuity cannot be removed. So in such a case f of x does not exist. So if f of x has irremovable discontinuity, if f of x has removable discontinuity, then f of x or lim of f of x lim of f of x does not exist, does not exist in such case. So we have another property. The another property is sine functions and cosine functions. So sine functions and cosine functions have uh, the continue are continuous for all real values of x, or we can say for all values of the x. Logarithmic functions are also continuous if log of x is greater than 0, then it is continuous for all x greater than 0. Exponential functions are also continuous except 0, and constant functions are also continuous for all the values of x. So let's start solving the sum. So if you like the video, please share, subscribe and comment on my YouTube channel, making maths easy. In the next video we will solve the sums based on limits. So thank you for watching.